Okay, so we continue natural transformations, and the first thing we're going to discuss today is the Diomedes lemma. It's one very famous and important statement from the category theory. So I assume that I have C, some category, so C is a category, and with any category I want to relate another category, so C with a check, and this will be just by definition the category of all functors from the category C to the category of all sets. So then the lemma is the following statement. So for any functor, so in this case, with this notation, I can just write this as an object in this new category. We have the following. If I consider all the natural transformations, which I can just write again using this notation as a C with the check from the representable functor h sub a to the f. So this set of natural transformations is in the bijection. It's just the value of this functor on the object A. So this is bijection natural in A and F. Or in other words, if you prefer different statement, we can say that this is isomorphism of bifunctors, where we can interpret the left-hand side as a bifunctor and the right-hand side as a bifunctor. So from the category, when you choose an object A, this will be from the category C, and when you choose functor F, this will be in the category C with a check to the sets. Okay, so this is the statement. Well, what it means to be natural in A and F, we're going to see in the proof. So it will be some two commutative diagrams. So first of all, why we have this bijection? Well, maybe before I even start the proof, is the statement itself clear? Right? So we have some functor, which is a fancy notation to say that F is a functor from the given category C to the category of all sets, which is what we have. And then we study all the natural transformations from this particular functor, which is just sometimes called representable by an object A, to any given functor. It turns out that this is precisely the same thing as just the value of this functor on the object A. And it's not just a bijection, it's natural, but we're going to see what it means more precisely when we do the proof. So let's first of all establish this bijection. So if I have an element in this set on the left hand side, this is a natural transformation, and the natural transformation by definition we have the following commutative square. So I can write h sub a of A so that's a component of a natural transformation. Now here I apply the first functor to some map F. Here I apply the second functor to the same map F. And then I'll get h sub A from B. This is component theta sub B, and this is f of B. So here theta that I have is a natural transformation which lives in this C with the check h sub A F, right? And F is just a map from A to B, right? For any such map, I have the following commutative square, well, just because theta is a natural transformation. Well, if I write the formula that corresponds to this commutative square, I'll get the following. Functor f applied to the map little f. Then yeah, so suppose I also choose a particular element. So remember that this h sub a of the A is precisely just all the maps in the category from A to A. So there is a distinguished element, namely the identity that lives here. So I can take theta sub A and apply this to the identity of A, and then to the result I apply f of the little f. So I'm choosing the identity element here, the distinguished element here, and just going using these two arrows. And this is supposed to be the same, since this is a commutative square, as the theta sub b, which I apply to the h sub a of the f, again applying this to the identity on the a, right? The same commutative square, just applied to a specific element, one that lives in this set. Well, this thing we can simplify a little bit, right? So what happens if I apply this functor to the identity? Remember that the functor h sub a, when you do this with the maps, is just taking the composition with the f. So this whole thing is just nothing else but the f. So I can write this as the theta sub b of the f. So what we see from this formula is that, well, if I know, well, let me maybe just write so how bijection looks. So the bijection is the following. Natural transformation I can send to the value of this natural transformation component with the index a, which I evaluate on the element 1 sub a. Right? And from this formula we can see this is indeed the bijective correspondence. Right? Well, if you have a natural transformation, of course you can compute this thing, just very special kind of information that you can extract from natural transformation. And if you have this element, right, and you're interested in the component theta sub b for any object b and for any morphism f, well, you just use this formula. This thing is given, right? You can evaluate this part, and that will be the result theta sub b of f. So indeed we have a bijection. So now we need to understand why this is natural in both arguments. So let me say that now we discuss naturality. In A. Well, this just means that we have the following commutative square. So C with the check, H sub A F. Now here we have functor C with the check H sub F blank, which I also want to denote large H sub F. So as before, I assume that I have this map F from A to B, the same kind of map. Right, so then this I can identify by what I already know with the value of F on the object A, and this can be identified with the value of F on the object B. And here we have functor large F applied to the little f. Okay, so the commutativity of the square is precisely the statement that this is natural in A. Right? If you think about this, if natural in the argument where you put A more precisely, right? So here we have from the previous observation the bijection for an object A, this we have bijection for the object B, and these two bijections are not just two random bijections, they are related by this commutative square. Here we have this functor, and this is just functor f applied to the map f. So you can see that this large h sub f is like before when we discussed this little h sub a, but now, of course, this little h sub a also defined not just on objects but on the morphisms, but it's kind of on the next level. This is for functors, not for the objects in the category. Okay, so we need to show this, right? First of all, simple observation. Maybe I can write the proof right here on this blackboard. Well, if you apply this functor h sub f to some natural transformation theta, you by definition are doing the following. You just take composition of the theta with a little h sub f. This is how this thing is defined. Well, this is how we define such functors. Okay, now let's look at the condition that this square is commutative in terms of formulas. So I'm trying to write the formula. So take the composition of these two natural transformations, apply this to the identity on the B, right? So I'm going in this direction first again. Now, by the definition of the composition of two natural transformations, this is supposed to be the component with the object B for the theta. I take composition with the component of the h sub f again for the object B and apply this to the identity map on the object B. So the same argument as before. We know what this thing is doing to the identity, just taking composition with the f. So here we have just theta sub b of the f, and this is supposed to be equal. Let me just write an answer and then we see why this answer is correct. Right, so this last equality is what I want to get. I computed what I have if I go like this, and now I'm just writing what I have if I go like this, right? So by the Ioannidis correspondence, natural transformation theta here is sent to the theta, apply theta with component A applied to the identity on A, right? So this thing is the result of application of this map, and then I just apply this thing, f of the f. But clearly this is true, right? Because we already proved this. This is what we have in the previous proof. This in terms of formulas, it's precisely the same formula. Hence we have naturality in the object. So the last thing we need to check is the naturality in functors, so in f. Again, the neutrality condition is some commutative square, so in this case I need to fix a natural transformation, say alpha, from the functor f to the functor, say f prime. So natural transformation, so double arrow. That's a natural transformation. So then what I need is the following commutative square. So again, as before, on the vertical arrows, I just fix the Ioannidis bijection. And on the horizontal arrows, I just writing how these two bijections are related by this natural component of this natural transformation and taking composition with the natural transformation alpha. So neutrality is precisely commutativity of this square. Sure.
What means H sub H prime
Oh, that's a natural transformation. Well, maybe I'll write it here. So we continue to assume that we have this situation. We have map F between objects A and B, right? So then you have two functors, h sub A and h sub B, right? These are two functors representable by objects A and B. But then if you write them what they are, so these are in the category C, first object is fixed, something is...
This H is natural transformation
Yeah, and this is precisely, if you look at this, at the definitions, let me just finish this, maybe it's not, wasn't completely clear when I stated this. Right, so this was something by definition. Now, if you have a map from A to B, right, then you just can take composition. And this induces natural transformation. So for example, if you have a map from B to some C, you have a map from A to B, then to C, then you get a transformation from map from A to C. So it looks like that the transformation goes in this direction. So this is a natural transformation induced by the map F that I'm going to call H sub F. Okay, yeah, so the last step, the neutrality with respect to the functor. I think this is even much easier. So in terms of formulas, commutativity of this square just means the following. I have natural transformation alpha. I take composition with the natural transformation theta. I evaluate this on the 1 sub A. Again, for these two natural transformations, I take component with the object A and evaluate this on the identity for the object A. And this is supposed to be, if I just, so as before, this part corresponds to if I go this direction and this direction, and it's supposed to be alpha sub A, which is applied to the theta sub A, 1 sub A, right? So I'm just rewriting this commutative square as a formula. But you can notice this precisely definition of a composition of natural transformations. Hence, we proved Ioannidis lemma. Okay, so before we continue, do you have any questions about the proof and the statement? Okay, if you don't have questions, I'm going to raise at least the statement. Maybe before we continue the formal discussion, let me maybe relate this Ioannidis lemma to something that you already know. Probably the easiest thing that you already know is the following. What is the hom over some ring R from the ring to the module? I'm pretty sure that we computed something like this in the first year algebra. So R is a ring, M is a, say, right R module.
It's the same?
Yeah. So, and how this bijection works?
Like we are sending leads to
Yeah. So this whole map F that lives here is completely determined by the value of this map on 1, right? This is just the element of the module. If you have a map, you compute this. If you have an element from the module, you just define a map that satisfies this property and then just use our linearity. Now, another question would be, for example, if you look at the hom, say, now let me, instead of writing homs, use shorter notation. If I have a group, I consider the category of G sets and compute maps from the G, considered as the G set, to some other G set X. So what it is? You just use the same logic. Yeah, because this is again completely determined by where you send the identity element in the group, right? Because the map is equivariant, the rest is completely determined by the condition this equivariant map. Now I can do this for monoids, for example, and of course for monoids it will be exactly the same answer. So if in the category of monoids I can take a monoid and some set on which this monoid acts, it will be X. Well, but this is a statement of the Ioannidis lemma when your category is just a monoid. So Ioannidis lemma is kind of generalization to the categories of statements of this kind, where you compute Holmes and the first argument is something very simple. So this is one of the ways to think about the Ioannidis lemma, this analogy with what you already know from the algebra. Okay, but formally I wanted to say that I have the following corollary from the Ioannidis lemma, which doesn't really require a proof, it's so easy. So the functor h sub blank, so which I consider as a functor, so this is contravariant functor, so this will be functor from the opposite category of the given category C to the category of all functors from C to the sets. So this functor is fully faithful. Okay, so is it clear what the notation means? It means that I have category C, right? I take an object in the category C, and with this object I can associate a functor. So object is going to the functor H, so object A going to the functor H sub A, and that's a functor on the category C with the values in the sets. Notice that this functor is indeed covariant because I fixed the first argument, but the correspondence that associate this functor to the object is contravariant, and that's precisely this observation. Okay, so this means that you can always consider a category being fully faithfully embedded into the category of all functors to the sets. And the proof was of course very simple. Well, to say that the functor is fully faithful, we need to say that it induces bijection on the Holmes sets, but if we just do the computation, so take this Holmes set between two functors H sub A and H sub B, right? Now this is all the form that where the first argument is representable by H. Well, representable functor H sub A. So we can apply the Ioannidis lemma and simply say that this is H sub B applied to A, which is the same thing as the C between objects A and B. Okay? This is a very special kind of computation where not only the first argument is of the nice form, but the second argument is also some understandable nice form H sub B. Hence we can compute this Holmes, and we see that this correspondence from objects to the H sub object indeed is a bijection on the level of the Holmes sets. So any category can be fully faithfully embedded into the category of functors with values in sets. And now we can do this dually. So I can define C hat to be by definition all the functors from the category, all the contravariant functors. So from a category C to the category of all sets. So then the dual statement or opposite statement for the Ioannidis lemma is precisely the same proof. Well, we can formally say that we're going to the opposite category, will be the following, that the natural transformations from the contravariant representable functor to some contravariant functor f is precisely the value of this functor on the object A. Again, this is for any A or any f in the corresponding categories, and this is also natural in both arguments. So you can do the same proof, or you can say that you're going to the opposite category, and this is just Ioannidis lemma for the opposite category. Okay, so then we can restate the corollary and say that the H with the upper blank is a functor from the category C now to the category C with the hat. So this is again fully faithful. maybe a little bit nicer statement, because here you kind of embed the opposite category, so embed this in the contravariant way, but in that statement you embed this in the covariant way. But the price to pay is that you consider the category of contravariant functors as a target. Okay, and I want to finish this with the formal definition. A functor f from some category C to the category of sets is called representable or, to be more precise, by some object A in this category C if there is natural transformation, no, not just natural transformation, but natural isomorphism of functors, which give us the isomorphism between the given functor and the functor h sub A. So this theta give us isomorphism of functors. So this H with some object, these are called main representable functors, and any functor isomorphic as a functor to these functors are also called representable. Just a definition. Okay, so that
why in this corollary the space of all function or natural transformation between functors is the same as the space of functions from A to B and not from B to A? Shouldn't they be switched? Or
yeah, it may be correctly. So let's look at this. Yeah, you're right. Yeah, sure. Of course, this from the definition H with the lower B, we suppose in the home set just fix the first argument B, right? So then here you'll get B and A. That's right. But so the statement is still correct because I have this opposite, right? So this is precisely why I need the opposite, because of this switching disorder. Okay. So this was the Ioannidis lemma, and next topic from this section will be the horizontal composition. So the horizontal composition of natural transformations, and sometimes it's also called in the literature Godemann's product. This was the first person who introduced this, I think maybe 80 years ago. Okay, so the situation is the following. We have three categories. Let me call them A, B, and C. So I have categories A, B, and C. And then I have functors. So here I'm going to call functors F and G. Then there is natural transformation alpha between these two functors. And for categories B and C, there is another pair of functors. I'm going to call them H and K. And there is a natural transformation beta. So this is the data that we consider. Three categories, four functors, two natural transformations. Okay, so then we can kind of associate to this diagram a diagram where I have category A, category C. And then here, of course, I take composition of functors. So this is a composition of the functors H and F. Here again, just the composition of functors K and G. And on this composition of functors, I'm getting a new natural transformation that I'm going to call beta star alpha. So you kind of see the reason why this is called the horizontal composition, and the standard composition of natural transformations is called the vertical composition. Well, the goal now is to define this. What is B star alpha? So I need to define this operation. to do this, let me fix component alpha sub x for the natural transformation alpha. So this is from the f of x to the g of x for any object x in the category A. And then, using that the beta is natural transformation, I can write the following commutative square. I have h and f, which I apply to x. So here I have component of the natural transformation beta for the object f of x. So this goes to the k f of x. Now this will be the map where I apply functor h to the alpha sub x. So this will be the h g of x. Finally, this will be kg of x, k of x. So I'm just writing a diagram saying that beta is natural transformation for this map. Okay, so we have this, and now by definition, say this is definition, the beta star with alpha, it's a natural transformation such that by definition its component for the object x is this map or this map. So since this is commutative square, any way to go works. So this is we just as we want, this will be natural transformation from this object to this object, or more precisely from this functor to this functor. So this can we say this is beta sub g of x composition with the h of the alpha x, or equivalently we can think about this as the k applied to the alpha sub x composition with the beta f of x. So this is the definition. So let me just say several formal things about this construction, and then later I'm going to explain why this is indeed an interesting operation of natural transformations. Okay, so let's look at the special cases. In the first special case, I can take f to be the same as g. Right, so, well, take a to be the same as b, of course, and the functors are the same. And the natural transformation alpha is just the identity, natural transformation on the functor f. So then we can define the following kind of composition of a natural transformation and the functor, but this is understood precisely as the horizontal product of the natural transformation beta and the identity natural transformation on the functor f. So whenever you see this kind of product of a natural transformation and functor, this is what it means by definition. So this is natural transformation from the hf to the kf. Or more precisely, if we want to understand this for components and objects, this is not so hard to do. If you just look at the definition, this will be a beta, but its component not just x, but the f of x. Also, sometimes people for shortness write something like this. So formal notation for this would be beta f is the same as f sub b. You can write such formulas just to remember what we're doing. So this one special case, and of course you can do kind of the corresponding special case where you take h to be equal to k and beta in this case to be just the identity natural transformation for the functor h, and then we will get the composition in the other order. So h composed with the alpha, which will be by definition identity natural transformation for the functor h, horizontal product with the natural transformation alpha. So that's the natural transformation from the functor hf to the functor hg. And if you want to understand this again for objects, you can write that the h alpha of x, this is h applied to the component alpha sub x. Okay. So this, I'm introducing these special cases because I'm going to use these notations from 1 and from 2 later for other statements. 3, a very special case. Probably I won't use this, but anyway, I'm going to do this. Now I assume that h is equal to k and g is equal to f. So then I can define the product with the star between two functors. And by definition, what it means is just taking the horizontal product for the identity natural transformations first for the h and then for the f. Just a definition. Okay. So now let me go back to this commutative diagram, and what I'm going to do is just rewrite this commutative diagram but removing object x. So then I'll get the following using what I already introduced in the notation. I have composition of the functors hf. Here there is a natural transformation beta sub f to the kf. So this is h alpha, and this is k alpha, and this is hg beta sub g kg. So you can look at that commutative diagram, look at these two definitions that we have here and here, and you'll see that this is precisely what I get if I plug in these two definitions into that commutative diagram. So from this commutative diagram, I can write the following formula, that the beta star alpha, I can compute this in two ways. I can write this as the 1 sub k composition, sorry, not composition, but the horizontal product with alpha, and then composition with the beta horizontal product with one identity on the f. Or another formula will be more or less the same, but we first have beta star 1 sub g, and then we take composition with 1 sub h star alpha. Just rewriting the same commutative square, but in terms of formulas. Right, so by definition beta star with alpha is a map, the diagonal map, and I can compute this diagonal map in two ways. And this kind of formula, this is the main computational tool when you think about this horizontal composition or horizontal product. For example, from this you can derive, well, first of all, you can, with this, maybe even without this, you can derive the statement that this product is associative, but that's not very interesting. It's more or less clear. So maybe let me formulate this as a proposition, but I'm going to leave proof as an exercise. So on the proposition, I have two properties. That first of all, the star product is associative, and second property, a little bit more interesting, that the star product is too associative or satisfies the interchange law. So horizontal product is too associative, or equivalently we can say that, so, or we have the interchange law. And the statement is the following. Okay, so it looks like I changed my notation a little bit, but so let me repeat this. I have A, B, and C. These are three categories. As before, I have functors, but now I'm going to call, oh no, now I have not just 4 functors, I have 6 functors. Yeah, and this is the reason why I need to change notation, otherwise I'll get too many letters. So let me call this functor F, this will be functor G, and this will be functor H. And then between these two functors I have two natural transformations, alpha and alpha prime. Right, so this is G. And this is F prime natural transformation. No, sorry, this is not alpha prime, this is beta. So now this is alpha prime, this natural transformation is beta prime. So this functor in the middle is going to be G prime, and this last functor is going to be H prime. So this is my notation now. So 3 categories. So here I have 3 functors, F, G, and H. Again, 3 functors, F prime, G prime, and H prime, and 2 natural transformations, alpha beta, alpha prime, beta prime. So with this notation, the interchange law or two associativity tell us that the following formula holds. So beta prime, take composition with the alpha prime, then take the, so this is the standard composition of natural transformations, the vertical composition, and then take the horizontal composition, and this is the same as the beta prime star beta composition with the alpha prime star alpha. So this is just the identity of natural transformations from the F prime F to the H prime H. Okay, maybe it's not clear. So this is the formula. So this is the data that we have, and this data satisfies the formula. So the proof is an exercise for the seminar. I can give you immediately a hint. So everything is based on just application of this formula several times. Okay. So these are formal things, and now we can look at this from the different perspective. So for the categories we have this kind of hierarchy. We have, say, 0 categories, and this will be by definition the same thing as the discrete categories, and this is the same thing as sets. Just by definition. And so we think about the sets as a very special kind of categories where you don't have any arrows, just objects. Now then we have 1 categories.